Okay, this is going to be a video on concavity. So concavity right here I have defined. Concave up is if f prime is increasing on some interval I, and concave down is if f prime is decreasing on some interval I. So to understand what that means intuitively, I plotted a couple graphs here, but before I get to those graphs, I'm going to plot a little bit of a simpler graph. Now this graph is going to have a parabola, can be whatever kind of parabola you want. But it's going to be a parabola. Why is it making this white? Okay. We're going to have a parabola, and it's going to look like this. That's not... Okay. Okay, the derivative of a parabola is a linear graph. In this case, it's just going to be this. And let's make sure it's going through the origin. Okay. Okay, so what we have here is some parabola and a quadratic function, and then we have its derivative. Now, typically what we can discern is f prime tells us how f is behaving. When f prime is negative, we know that f is decreasing. When f prime is positive, we know that f is increasing. We can see that on the graph we just made. When this green line here is below 0 on the y-axis, we can see that f is decreasing. It's going down. But when it's above y equals 0, we can see that it's going up, going back up. Similarly, f double prime tells us the same thing, but about f prime. Now, the derivative of this just line is going to be some positive constant. In this case, we don't have a defined number, so I'll just make it right here. And you can see here that f double prime is always positive. So if we're using the same logic about f prime and its relation to f, then if f double prime is positive, that means that f prime is increasing. And we can see that's true because f double prime is always positive, and we can see that f prime is always increasing. Now that may not always be the case, but for this little example, it is the case. Now likewise, if we look at f double prime, we can see it's always positive, and we look at f, we can notice one other thing. The words I use to describe this may be a little vague, but when I say that f is always increasing its slope, if that makes any sense. You can see that without f double prime, you can just see that f prime is always increasing by looking at the graph. But if you look at the tangents next to this quadratic, you can see that the slopes are always kind of going up, right? All the way to the end. They're always increasing. They may be negative initially, but they're becoming less and less negative until they're positive, and they're becoming more and more positive. If that makes any sense, I hope it does. So you may not necessarily need f double prime to tell you that. You could have just looked at f prime and discerned that yourself. But f double prime tells us that. And when we get into more complicated graphs, you'll see why that's useful. So just to quickly discern this parabola, we can conclude that this is concave up because f prime is increasing on this interval. Okay, moving on. Let's look at this other graph I made here. Now over here I have f is x cubed, f prime is 3x squared, and f double prime is 6x. Okay, so looking at this, it's a little bit more complicated, but it's the exact same idea. F prime, which is 3x squared, is always positive. This parabola is always positive. It's always above y equals 0. And that means f is always increasing. And we can see that here. It may be increasing at different rates, but it's always increasing. It's never going down. Okay. Again, similar logic. F double prime, we can see it's actually negative in some parts and positive in others. And likewise, if we look at f prime, we can see it's decreasing in some parts and increasing in others. And these parts, of course, correlate to one another. When f double prime is negative, we can see that f prime is decreasing. When f double prime is positive, we can see that f prime is increasing. Now, if we look at f double prime and we look at f, when f double prime is negative, f actually is concave down. When f double prime is positive, f is concave up. Now, that may not mean anything to you, so let me hopefully try and convince you as to what that means visually, so where you can kind of identify it. Concave down is typically going to look something like this, like an upside down U. Concave up is going to look something like a U. You can say a frown down, cup up. That's an acronym I heard, or like a saying I heard, I mean. Okay. So understanding why those are given their own thing, again, look at their tangents. You can see that in this concave down example right here, the tangents are always decreasing. Again, they can be positive and negative at different parts, but the thing you need to focus on is that they're decreasing. Their gradient is becoming less and less. They may start out super duper negative or super duper positive, but they're decreasing or they're increasing. In this, for concave down, that means they're decreasing. In this case, you can see it's starting out super duper negative, but it's slowly inching positive, and then it ends up being super duper positive. Now, there's no limit to the times which you can flip between these. You can flip between concave up, concave down on multiple times on the same graph, doesn't matter. And the point between these is called the inflection point, or the point of inflection, which is literally just defined as the point between where f double prime is 0. So on either side, that means it's going to be positive or negative or positive, concave up or concave down, whatever. But getting back on point, we can see the left side of this graph, x cubed, is actually going to be concave down if we look at the example I drew down here. The tangents are decreasing. Likewise, f double prime is negative, so that's something that tells us that. And if we look at f prime itself, we can see its tangents are even decreasing. So it makes even more sense. And on the other side, it's complete same idea. F double prime is positive. F is concave up. Now, you'll notice we had concave up, concave down. So where do they switch? And like I said, the point they switch is called the point of inflection. And that happens, in this case, at 0. And f double prime is 0 at 0. 6 times 0, because it's a 6x, that's our graph here, is going to be 0. And that is the point of inflection. So that's kind of a rundown of kind of what concavity is and how it applies to interpretations of graphs. F double prime, F prime, and F, these are all super duper important parts of not only graphing functions, but understanding how they change over some interval.